This is part 7 of the series Reasoning and Proof. In the last part, we worked through a fairly detailed example of a basic proof to discuss how to do a two-column proof, the process of how to plan for your proof, how to lay out the steps using the reasons as your guide. What we're going to do now is we're going to look at a couple of new properties, and we've looked at properties of equality. Now we're going to look at properties of congruence. Specifically, we're going to look at some properties of segment congruence. So let's start off with the first one. And we have the reflexive property of segment congruence. So here we have the reflexive property of segment congruence. The abbreviation is generally the word reflexive and then POSC, property of segment congruence. You are perfectly welcome to write out the entire definition if you wish, or the entire name, but I generally opt towards the lazy side, and this is what I'll usually abbreviate. Here it is. Segment AB is congruent to segment AB. Remember before we had some letter equal to some letter, or some number equal to some number. So we had the reflexive property of equality. This is the reflexive property of segment congruence, where we have two of the same segment on both sides of the congruent symbol. The same thing is true for the reflexive property of angle congruence. Here it's POSC, property of segment congruence, property of angle congruence. Angle A is congruent to angle A. Again, it's not going to be terribly obvious until we actually use it. I will highlight the reason for using it when we actually do, but it will come in very handy. These reflexive properties are not just trivial, they're actually very useful. So that's reflexive property. And so you can say that segment congruence is reflexive. That's what this property is telling us. So let's look at the next property. This is the symmetric property of segment congruence. And here, symmetric property of segment congruence and the symmetric property of angle congruence. Symmetric property of angle congruence. So here we say, if segment AB is congruent to segment BC, then segment BC is congruent to AB. This is what we talked about before, swapping sides. You have the ability to do this with segment congruence and angle congruence as well as with equality. So these things can be swapped from side to side. And it's really more for organizational purposes when you're working through proofs. If you're actually trying to prove that segment BC is congruent to AB, but you have a statement saying AB is congruent to BC, you can use the symmetric property to swap the sides for those two statements. It may seem, again, it may seem trivial, but form is everything. The details are what geometry is made of. And once you get those details down, it's really not that difficult. So we have reflexive property and symmetric property. So now we know that segment congruence is reflexive and symmetric, and angle congruence is reflexive and symmetric. Now let's look at the third one, which was the transitive property. Now we used the transitive property in the last proof we did. That was the transitive property of equality. So equality is reflexive, symmetric, and transitive, but now so is segment congruence. And here we have, if segment AB is congruent to BC and BC is congruent to CD, then AB is congruent to CD. AB is congruent to CD. Do you see that same pattern forming here with A equals B and B equals C, then A equals C? The same thing applies with these things. So here we have transitive property of angle congruence. If angle A is congruent to angle B, and angle B is congruent to angle C, then angle A is congruent to angle C. Angle A is congruent to angle C. Transitive property is very closely akin to the law of syllogism in logical laws. So now we have three new tools for our tool belt, if you will. we know now that equality is reflexive, symmetric, and transitive. Segment congruence is reflexive, symmetric, and transitive. And angle congruence is reflexive, symmetric, and transitive. So we can use those properties on all three. Now this is one of the keys for why you have to use these abbreviation codes, because now we have three different reflexive properties, three different symmetric properties, and three different transitive properties. We have one for equality, one for segment congruence, one for angle congruence. So it's important that you distinguish which one you're using. It's not enough just to say reflexive. You have to say reflexive property of segment congruence. If you're dealing with segments, if you're dealing with angles, it's angle congruence, and if you're dealing with equality, it's equality. So let's go ahead and put these into practice and work another proof. We're going to prove the symmetric property of segment congruence. It's a fairly straightforward proof, but it'll give you an idea of how to use these proofs. And again, the key to proof is practice. So here we're given segment AB and segment CD. These little hash marks indicate that segment AB is congruent to segment CD. What we want to do is we want to show that CD is congruent to AB. In other words, we want to show that we can swap the sides of these two things. Now I know that I gave you that property, but whenever we're dealing with properties and theorems, we have to be able to show that they're true first. We can take them on faith that they're true because someone proved these things a long time ago. But what you're going to see is we're going to be proving many of the theorems that we're going to be talking about. And it's important to understand where these things come from because it'll give you a greater insight in how to use them. So let's, as usual, let's take a look and absorb our information. We're given that this is congruent to this, and we have to prove that CD is congruent to AB. Well, we know where we're coming from and what we have to get to. Let's think about what this tells us. What does this given information tell us? Well, I know that if two segments are congruent, since I know the definition of congruent segments, two segments are congruent if and only if their lengths are equal. So I know that the lengths of these two segments are equal because they're congruent. And I also remember that I have a reflexive property, a symmetric property, and a transitive property of equality. So since I need to take these and swap sides, and I can't use the symmetric property of segment congruence yet because I haven't proved it, I'm going to have to use something else to get me to that point. So since I do have the symmetric property of equality, I'm going to go ahead and use that to show that I can swap the sides of these two segments. So let's begin. As usual, I'm going to write down my given. Now I had said that because these two are congruent, that tells me that their measures of these, the lengths of these segments, are equal. So that's going to be my next statement. I'm going to say that AB equals CD. And that's the definition of congruent segments. So because I know the definition of congruent segments, I can write the length of AB is equal to the length of CD. Now I have to get the CD on the left and the AB on the right. So I know that I have equality is reflexive. So I can swap sides using the reflexive property of equality. And so I stated CD is equal to AB, and the reason I can do that is the reflexive property of equality. Again, these statements are driving, these reasons are driving the statements over here. Now I have to go from equality here back to segment congruence. Now up here we went from segment congruence to length equality, and the reason was definition of congruent segments. Remember that all definitions are biconditionals, which means that their converse as well as the conditional are true. So I can say, if two segments are congruent, then their lengths are equal. I can also say, if the length of two segments are equal, then those segments are congruent. So to go from congruence to equality, or from equality back to congruence, it's always the same. It's the definition of congruent segments, congruent angles, whatever it happens to be. So that's what I'm going to write. And there you have it. Because I know by the definition of congruent segments, if their lengths are equal, the segments are congruent. And I've just proven what I was trying to prove. So as I said, it's a fairly simple proof, but it gives you an idea of how to think and how to work through these proofs. We did the same thing we did before. We analyzed what we were given. We discussed where we had to go to, and we came up with a basic plan for how we go from here to here, and that plan fell from the properties and the definitions that we knew about. Now we're going to take the next logical step forward. We've worked with definitions and postulates. The next thing to talk about is something called a theorem. A theorem is nothing more than a statement that may not in and of itself be intuitively true, but it can be proven true. Now, the key for theorems is once theorems have been proven true, they are for all time usable as defined facts that we can use in our tool belt to prove other things. They now become new truths for us. The first theorem we're going to look at is the right angle congruence theorem. The right angle congruence theorem says quite simply, all right angles are congruent. Now, it should be fairly intuitively obvious to you that these two are going to be the same angle, but this is kind of a trivial example, but it's a good way to step off into the world of theorems to show you why these things can be proven true. So let's see why this is true. So we have angle 1 and angle 2 are right angles. And we have to prove that angle 1 is congruent to angle 2. So again, to plan for our proof, what we do is we think about what does this tell us? Well, if these are right angles, then we know that their measures are 90 degrees. And if their measures are both 90 degrees, then the measure of these two angles are equal. And since I know that the measures of two angles are equal, then those angles have to be congruent angles by the definition of congruent angles. So I knew that if they're right angles, then their measures are 90 degrees, and that's the definition of a right angle. And since both of these measures are equal to themselves, then those two angles have the same measure, and because the angles have the same measure by the definition of congruent angles, those angles are congruent. So let's go ahead and write down those steps starting with the given. So here I have angle 1 and angle 2 are right angles, that's given. Now this tells me that the measures of these two angles are 90 degrees by the definition of right angles. So that's what I'm going to write. So because the definition of right angles means that the measure of angle 1 is 90 degrees and the measure of angle 2 is 90 degrees. Now you should see a familiar pattern forming here. If A equals B and B equals C, then A equals C. That's right, transitive property of equality. And it's equality because we have an equal sign here. So if this equals this and this equals this, then this has to equal this. So that's transitive property of equality. And of course the reason I did that is because I have to have angle 1 on the left, some symbol, and angle 2 on the right. It just so happens that our symbol is equality. Well, remember that we know by the definition of congruent angles that if two angles have the same measure, then those two angles are congruent, and that's what I'm trying to find. So that's my last step. And there we have our proof. Angle 1 is congruent to angle 2 by the definition of congruent angles. Again, this right side drove the left side. Because I knew these definitions and these properties, I was able to come up with these statements because I was guided by what these statements are telling me. In the next part, we'll go ahead and look at some other theorems that will further help us out. So I will talk to you in the next part.